interesting. All right. Um, so based on what we've talked about the last couple of lessons, we know that this equation plus a1 x y prime plus a0 of x y equals 0. And we're assuming that our coefficients satisfy our conditions. So we know that this has a solution. And our solution looks like this, C1, Y1 plus C2, Y2 on some interval. Where Y1 and Y2 are linearly independent. So that's basically what we've talked about the last 2 days, is that an equation like this is going to have a solution that looks like this. Sometimes when we go through our process, we'll see that tomorrow, we can only find one of these solutions. Computer's running particularly slow this morning. I got a new computer.
You did?
But I have to install, well, I have to get an IT person to install all the software that I need, because I'm not allowed to install the software. Yeah. Because sometimes teachers install software that's compromises the security of the network, which happened once in the past. We used to have a network drive, and someone did something, and the network drive, the entire network drive went down. So nobody could access their files.
Wait, what? What did they download?
I don't know what happened, but they had something, they ran something on their computer that infected the whole system. So they don't trust us anymore.
How long ago was this?
It was pre-COVID.
Okay.
But now everything's on Google. But anyway. So sometimes we can only find one of these two solutions. So we make a substitution. Based on the known solution to produce a first order linear differential equation. That can be solved to find the second solution. And this is kind of in differential equations, it's kind of a theme. If we know how to solve one type of equation, often we'll make a substitution to turn a different kind of equation into the one that we know how to solve. We turn the problem into one we already know how to solve. And making some kind of clever substitution is often the route that we use. So that's the idea for today. I'm gonna show the process of this, making the substitution on the solution. It's all based on stuff that we have learned, and it's not difficult to understand. But we'll come up with a kind of a formula, I guess, if you want to think of it that way, that we can use for reduction of order. But I want to show the process because it all involves stuff that we already know. All right, so our process. So we start with a2y double prime plus a1y prime plus a0y equals 0. And we know a1, a2 and a0 are functions of x. So we're going to divide by a sub 2. So we get y double prime plus, and I'm going to write it this way, p of x y prime, where p of x is a1 divided by a sub 2, plus q of x y, where q of x is a0 divided by a sub 2, equals 0. So now we have our second order differential equation written in standard form. And we know that p of x and q of x are continuous on some interval because a1, a2, and a0 are continuous on some interval. And now we suppose that y1 of x is a known solution. And that this is not the trivial solution. And I'm going to let y be some function u of x, y1 of x, be our other solution. So we're assuming that our other solution is some product of this first solution. Well, this tells us that, I'm just going to take derivatives now, y prime, using the product rule, uy1 prime plus u1 prime y1, and y double prime equals, using the product rule again, we get u y1 double prime plus 2 y prime u prime plus y1 u double prime. And now we're going to substitute. We're just substituting these derivatives into our differential equation. Well, y double prime is this whole thing. So we get y1 double prime plus 2 y prime u prime plus y1 u double prime plus p of x times y prime. So I'm just going to write that as p times this, u y1 prime plus u prime y1 plus q of xy. I'm just going to write that as q times y. That's u y1. And that equals 0. Well, I'm going to gather some terms and rearrange this a little bit. So this is going to equal, this left-hand side, I can write as u times y1 double prime plus p y1 prime plus q y1, just y1, plus y1 u double prime plus 2 y1 prime plus p y1 times u prime equals 0. So I just gathered all the terms that have a u, all the terms that have a u prime, and all the terms that have a u double prime. Well, this equals 0 because y1 is a known solution to this equation. So that whole term equals 0. So what we have is y1 u double prime plus 2y1 prime plus p y1 prime, not y1 prime, just y1, u prime equals 0. Now I'm going to let, and we did this in a couple of homework problems, we're going to let w equal u prime. So I have y1 w prime plus 2y1 prime plus p y1 w equals 0. This is linear and separable. So w prime is dw dx. So I can write this as dw over w plus 2y1 prime over y1 times dx plus p of x dx. And that equals 0. And we're saying w prime is dw dx. Well, I'm going to put this p of p dx on the right-hand side. So I have dw over w plus 2y1 prime over y1 dx equals negative p dx. And now I can integrate. Well, this is the natural log of the absolute value of w plus 2 natural log y1 equals negative integral of p dx. Well, I'm going to combine these together and use turn this 2 into an exponent. So I get the natural log of w y1 squared equals negative integral of p dx. I'm going to exponentiate both sides, e to the power of this, e to the power of this. And I'm going to drop the absolute value here. I get w y1 squared equals, and I get a constant of integration here, so this becomes c1 e to the negative integral of p dx. And we know that w equals u prime. We get that u prime equals c1 integral, u, so I'm dividing both sides by y squared and integrating because w equals u prime. We want to solve for u. U is c1, I divide by y1 squared. We're integrating e to the negative integral of p dx over y1 squared dx plus c2. So this gives us our u that then we multiply by the original solution, because we said, go back here, we said that our new solution is u times y1 of x. This gives us our u that we multiply by our original solution to get our second solution. And I think it's interesting that this e to the negative p of x dx shows up in this reduction of order. All right, so there's our process. Our process is based on things that we understand, substitutions, first order differential equations, separation of variables. So we're going to state this as a theorem, and that's where our formula comes in. Any questions on our process here? Okay. So our theorem on reduction of order, we're going to say suppose y1 of x is a solution to y double prime plus p of x y prime plus q of x y equals 0 on some interval. And that y1 is not equal to 0 for all x in the interval. y2 of x, here's our formula, equals y1 of x times that integral that we just talked about. The integral of e to the negative integral of p of x dx divided by y1 squared of x dx, and then we have a constant of integration implied in there. This is a second solution. On the interval. Yes.
What happened to the constants that we got from deriving an interval? We got two constants. Are those?
So one of the constants is going to be the constant that comes out of this integral.
Oh,
The other constant gets absorbed into the constant with y1 because we're multiplying those two together. So this is how we find, this is our reduction of order formula, if you like to think of it in terms of formulas. That gives us our second solution if we have a known solution. And often, when we solve higher order differential equations, we get a single solution, or we get a repeated solution, and we need to find new solutions. We find our new solutions using reduction of order. And what happens is the solutions take on a particular form, and we can just look at the solution and say, oh, by reduction of order, the new solution is this. So for a lot of the solutions we get, we won't actually have to do this integration. We'll say, oh, the reduction of order gives us this. Reduction of order for this one gives us this. And it's very easy to recognize. And we actually turn that recognition, we turn into kind of rules about our solutions. So I just want to go through one example of using reduction of order. So x squared y double prime minus 2x y prime plus 16y equals 0. And we know that y1 equals x squared is a solution. And I talked about this kind of equation last time. I think this is a Cauchy-Euler equation that we won't learn how to solve in this class, but similar to a technique that we will use in this class. So I'm going to rewrite this in standard form. I'm going to divide everything by x squared. So y double prime minus 2 over x y prime plus 16 over x squared y equals 0. So there's our standard form. P of x is negative 2 over x. So our second solution sure I have enough room here. y2 of x is our first solution, x squared times the integral of e to the negative integral of negative 2 over x dx over x squared squared dx. Do I have everything in there right? E to the negative p of x, yes. Okay. So e to the integral of 2 over x dx is e to the 2 ln x I think I want this to be positive based on how I solve this. Yes. That's why I was hesitating. So this should be negative, this should be negative, which is e to the, sorry, which is x to the negative 2. Use properties of logarithms, so I get x to the negative 2. So we have the integral of x to the negative 2 over x to the 4th dx, which is the integral of x to the negative 6 dx, which is minus 1/5 x to the negative 5. So y2 is x squared times negative 1/5 x to the negative 5th, which is negative 1/5 x to the negative 3. That's our second solution. And our general solution is y equals c1 x squared plus c2 times, I could write this as negative 1/5 x to the negative 3, which is the same as saying c1 x squared plus c3 x to the negative 3. And now we have our general solution to that equation, given our known solution. And I figured out why I confused that plus and minus. I had originally written down a different example and erased it. In the original example, it was minus 2 something, and then when I rewrote this, it was supposed to be plus, but I kept the minus from the original. So that's why I got confused. All right, questions? And really, today's homework is basically practicing doing this thing. Yes?
Did it matter that it was a plus or a minus, or was it just?
It would have mattered. So I just had one negative here, so it would have changed. It would have changed the sign here.
Okay.
That's all it would change. But I had gone through the rest of the solution
Yeah.
with just one negative
Fair
there.
enough. No.
Yeah. And I was afraid I'd make a mistake if I tried to do it in my head. I'd carry it through the other negative in my head. All right, so now we have everything in place to actually start solving these second order linear differential equations with constant coefficients. And I'm excited for tomorrow's lesson because there's a thing that happens in tomorrow's lesson that, to me anyway, is kind of a big, was a big revelation. And if we need time to finish up the homework from previous, the 4.1 homework, I will collect, towards the end of the class, I'll write down I'll come and collect the homework.